All right, prepare yourself because this is tough. So when we're dealing with ternary compounds, we have to deal with number of oxygens for most and the charge for those number of oxygens specifically, and that makes things tough. One takeaway from ternary compounds, and the reason we would call these ternary is because we have a metal, and then in many of these cases we have at least two other nonmetals, so a total of three, and that's where we get that ternary kind of name for having three different elements. There are going to be some that have more than three, but again, this is that polyatomic class where you're going to have definitely more than two, and typically you don't end in IDE. We did say there was some exceptions, so notice cyanide ends in IDE there, and then hydroxide ends in IDE, as well as peroxide down here ends in IDE. So a couple of those going to end in IDE, and just going to kind of plague you because there's always exceptions to worry about, and those are a few of them. But just remember that most of these, and this is the clue to take away for the exam, most of these end in ATE or ITE. So notice that's the biggest difference with most of these ternaries is they have the ATEs or ITE endings. That's different from IDE. There's a positive one, ammonium. That's one's kind of exclusive on its own. But the big clue here is ATE versus ITE. And the easiest way to recognize the difference is notice ATE has more oxygens. ATE has more oxygens. And when we go from phosphate to phosphite, it too would have more oxygens with an ATE than an ITE. So even in this series here, notice that we have this per-ate, ate, and then this hypoite. Notice in all of these situations we have more oxygens. So eight's always going to have more oxygens. That's going to be a great way to educate your guesses for purposes of the homework and exams. So more oxygens on the 8, and then again, less oxygens for the ite is a great way to recognize that difference. There's a few of these that are a little bit easier to understand, and that's things like chromate versus dichromate. Notice chromate versus dichromate, that's really just one chromium versus two chromiums. So that's a little bit easier distinction on a multiple choice kind of question. Permanganate, so permanganate has manganese, makes that one a little bit easier to think about. Other ones are just pretty random, pretty tough, and we're going to try to give you a indication of that, of how to at least think about them in patterns. So things like acetates and cyanides, those are ones that you're probably just going to have to remember straight up, a permanganate, chromate, and dichromate, although those are a little bit easier. Say a peroxide. Most of the others, though, we can give you a nice little pattern to help you out. The pattern that I like to use is called T43. I actually borrowed it from the internet. I scan the internet and YouTube videos quite a bit to see if there's any new and easier ways to make information a little bit faster to learn for students, because if I'm a student, I want to enjoy life as much as I can, and if I can learn things quickly and enjoy life at the same time, that's what I want. So in this T43 kind of idea, notice T43 is just drawing these boxes. So when we say T, we're really just saying draw the letter T on the periodic table. And then we're saying draw the number 4 on the periodic table. And then we're saying draw 3 boxes on the periodic table. So that's what we mean by this looks like the letter T, this looks like the number 4, and this looks like 3 boxes. So it literally is just T, 4, and 3. And that's where that kind of pictogram comes from. So what does it mean? Well, on top of the picture itself, what it also means is if you're in the T box, you're going to have 3 oxygens. And luckily T has the first letter of 3, also for 2 as well. So it's not a perfect coincidence, but it is something that can help us to know that it's not 4 because 4 starts with an F. So really it's a choice of 3 versus 4, because even in the 4 box, we have 4 oxygens. In the 3 box, we have 3. So really it's just a 3 versus 4 issue. So notice as we look in the T box, everybody has 3 oxygens. As we look in the 3 box, everybody has 3 oxygens. And when we look in the 4 box, everybody has 4 oxygens. That's an easy way to educate your guess on a lot of these questions, because that's the major difference in the A, B, C, or D choices. The next thing we should realize is that everything that's in this T43 series is an ATE ion. So any one of these, we could just reduce the 4s to 3s or the 3s to 2s and turn 8 into ite just by losing oxygen. And that's the easiest way to double down on this information, is if we know T43 is, borate and carbonate and nitrate and silicate and phosphate and sulfate and chlorate and bromate and iodate and so forth, then we know that that's the magic number of oxygens to look for. And as soon as we look for those numbers, we either see them or we don't. And if we don't see them, we can probably guess that if we don't see that number, it's going to be a lesser number, and that's going to be an ITE. And that's the best way to probably approach this information. Otherwise, it's a lot of flashcards and not a lot of fun. So these are called oxyanions because they contain oxygen. The tricky part is how many oxygens. And I'm trying to give you a heads up with this T43 pattern that if you know that T43 pattern, you're going to know the ATE. A great way to remember that idea is oxyanions are 8 up. That's 8 up in the sense of you have to remember any of this probably, but 8 up is 8 is up on the number of oxygens. So when you're guessing and you see a 4 versus 3, remember that 8 is always up. 8 is always higher in the number of oxygens, and that's going to help you better your guesses to get through a lot of those homework questions if you don't memorize these in time. So notice down here with sulfate and sulfite, notice if 8 is up, 8's a higher number of oxygens. And notice as we go from 3 up to 4, we're going from ite up to 8. And then this 4 was part of the 4 box, and that's why sulfur was expected to have 4 oxygens. Charge-wise, turns out that the ATEs and the ITEs are the same charge as the IDEs as long as you're in the 4 and 3 boxes. They descend from -3, -2, -1. Turns out the T box is not so lucky, but it also ascends -3, -2, -1. But a lot of those will be done for you. Most of what you have to concern yourself with for the exam purposes would just be recognizing the number of oxygens. That'll be pretty safe for that information. Anytime you add hydrogens, you're going to take away a charge. The reason for this is because hydrogen itself has a charge. So if we're adding hydrogen, we're adding a plus charge. So if sulfate is SO4 -2, notice it becomes SO4 -1 because H plus canceled with that -2 and made it a -1. So anytime you add hydrogens, you're going to reduce the charge by 1. If you add 2 hydrogens, in the case of a phosphate or a phosphite, you're going to take away 2 charges. There could be a point where you take away all your charge, and that's when you get into acid namings, which we'll deal with at the end of this chapter. So hydrogens are a little bit nicer in the sense that you're not changing the ion at all. You're just changing its charge because you're adding positive charges per hydrogen atoms that you're adding. It is true, though, that in the old system, hydrogen was named, and I hate this for you guys, but hydrogen was named for bi. So bi and hydrogen are the same thing. So hydrogen carbonate is the same thing as bicarbonate. That's just an improvement that they went from bi to hydrogen to make it a little bit easier. But a lot of companies using those old names still use bi instead of hydrogen, so be careful. Bi is not di, where it means 2 atoms. Bi is hydrogen. So it is a weird exception. It's a weird old rule, but a lot of those compounds still used today if you look at a lot of ingredient labels. So let's look at a couple examples. We have sodium. That's not so bad. We can find that straight off the periodic table. And all sodiums have a +1. Turns out nitrates and nitrites also have a +1. But again, notice the difference. If this were just NaN, not only would we cross a 3 and cross a 1, that would be a sodium nitride because it's binary. It has two elements, IDE ending. But notice here, because we have 1, 2, 3 elements, now we end in ITE or ATE. Just notice that if we go to more oxygens, that's when we become the ATE. It's always 8 up because you're getting more oxygens with that higher prefix of ATE. It's kind of like ichnos in a sense, where ich is the higher charge here, 8 is the higher number of oxygens. If they're mean, they'll throw the worst of both worlds where you have to deal with copper. Again, when in a situation like this, you could probably reverse to kind of get a clue. So if you take this 2 and bring it back to copper, that'll tell you that it's copper 2. Then it's a matter of realizing that there's copper +1s and +2s. +2 is higher, so +2 is ich. So that one's going to be tougher, obviously, because you have to deal with transition metals and you have to deal with polyatomic ions. The big clue here, though, is your nitrogen had 3, not 2. And because it has 3, not 2, notice it was 8, not 8. So a lot of things to worry about, but also a lot of things that you'll get to practice in the homework and in the extra credit and in some of the labs that we do together. Sometimes when we name compounds, we get to very large formulas. So in this situation, they're kind of showing you the basics of, behind the scenes crossover rule. If you have a 2 charge, you would cross it over. If you have a 3 charge, you would cross it over. And when that happens, notice the 3 next to magnesium is just fine, but what we don't want is PO42. We want PO4 twice. That's why we're adding parentheses to distinguish that 4 from that 2, so that we only have 8 oxygens and 2 phosphorus, not 1 phosphorus and 42 oxygens. So parentheses are required when you do ternary kinds of compounds, or ones that are even larger. And that's because if a number that's not a 1 goes to a polyatomic, we want to separate that polyatomic from its subscript, and the only way to do that is with parentheses. So ammonium phosphate. So ammonium is a tough one. Phosphate is a tough one. Ammonium is the only positive ion, and we drew it earlier this chapter. It's NH4 + 1. It's the only IUM that we really cover ion-wise. There is a hydronium, but we'll see it in the acid-base chapter much later in this semester. And then phosphate. Clues here is phosp is phosphorus. Because this is ATE, it has some number of oxygens. If we look at the periodic table over in that cute little P block, we have this T box, we have this 4 box, and then we have this 3 box. So there's our generic periodic table. What you're going to notice about phosphorus is right here. It's in what we call the 4 box. And by recognizing that, those are 8s. 8s come from T43. And if they come from T43, that means this is a 4. And as we look to the noble gases from family to family to family, we did this before. This family has 0 charge, -1, -2, -3, and carbon has -4. Phosphorus has a -3 regardless if it's by itself with 4 oxygens or with 3. It's a coincidence, but we'll take it. Remember, it's only the T box, it's only this group up here that doesn't follow suit. Those guys go back through that -3, -2, -1 in their 8 ions, different from the 4s and the 3s that follow suit with their binary ions. So let's assuming, using the patterns and some practice, you can get this far. Once you get this far, this is where you cross charges. Bring this one over, and then bring this one over. When you bring this one over, it's going to look like NH43. So to prevent 43 hydrogens from occurring, we want NH4 3 times, we use parentheses. And then we have the phosphate ion once, so we don't need parentheses to put a 1 outside of it. That's kind of redundant and overkill. That's a taste of polyatomics. A little bit tougher, obviously, because you're really looking for a number of oxygens, looking for charge. Charge is a little bit of a coincidence for most, but definitely looking for oxygens, always ATE, the higher number of oxygens is what we care about most. And then we'll come back in a final video for this very long chapter, and we'll talk about acids, which are pretty tough as well, especially for those that are ternary.